Hello, welcome to Bare Metal Machine. I'm Jeff Audia. I've been machining these parts today, and before I machine the last one, I thought I would stop and give a little demonstration on how I'm doing this. Doing what, you might ask? Well, machining a part that clearly looks like something that's come off of a CNC machine, yet done on an ordinary manual Bridgeport type knee mill. And I've done a bunch of them too. And I'm holding tolerances plus or minus 1, plus or minus 2 in that neighborhood. Not that this part needs to be that fussy, but I'm getting that effect basically for free. And also without any in-process measurements or adjustments, or even needing to know what the dimensions are. So the process begins with a blank, and just with the 3 holes drilled in it. And you end up with a part like this by turning cranks on a manual machine. How is that possible? Well, it's possible with a thing called the Tactical Cartesian Display, which is a computer system that's basically an augmentation to an ordinary DRO. And as you can see, I've already got the part model in the display. And the part started out life as an ordinary CAD drawing. I did this in TurboCAD. And then the model is transferred into the display. So now the display has an exact mathematical model of the part you're going to machine. And you see that little circle there to the left, that's actually represents a cutter of a given size. So everywhere I move the hand crank for the y-axis, say, you can see the cutter moving in real-time response to your machine inputs, and therefore you can see the tool moving with respect to your part geometry. The Cartesian display is not interfaced to the DRO. These two things are completely independent and unaware of each other. They just both share the same scale signals. In fact, the Cartesian display itself is actually a DRO. See, it says X minus 0.4677, and up here on the DRO we got minus 0.4677, and then 3.1039, and down here 3.1039. Okay, so the Cartesian display is like a mini DRO in itself, and you could use this thing all alone. It doesn't need the DRO. And also you can continue to use the DRO the way you always have. These things are totally unaware of each other. About the only thing they have in common is that when you set your origin and you set 0, 0 here, you need to set 0, 0 here on the Cartesian display at the same time. That way these two things are married to each other, but only in terms of the coordinate system that they share. Okay, now that I got my hands free, more specifically, what this thing does is, I showed you earlier how everywhere you move the machine, the representative cutter on the display moves in real-time response to your machine inputs. Okay, that should be clear enough. Now, you need to tell the display what size tool you're going to use. For instance, I'm going to use a 5/16 end mill in this work. So I'm going to go to Tools, and I'm going to pick 5/16. Bam. Right? It needs to know the size of the tool because it's going to be calculating the position of the tool with respect to the part geometry. Right? Remember, this is an exact mathematical model of the part, right, taken from the CAD drawing. So, now that you have the cutter set to the size you want, you can simply move it around with respect to the geometry any way you like, and the display will keep pace with your movements. And of course, your coordinates here will always match your DRO, and you're going to see in a moment that you really almost never need to know the coordinates of the tool. And the reason for that is because, well, for starters, you could machine a part just by following the lines like I just did. In fact, the nickname of this system is virtual scribe lines. But we can actually do a lot better. Okay, so remember that this is not just a picture of the part. It's the CAD drawing. It's a mathematical model of the part. Okay, and so that has an important implication. So let's say we're inside here, and maybe we indeed cut along this line to rough it out, right? But now we want to finish that line. We want to finish whatever dimension that line happens to represent. Okay, well, you could zoom in on it really close and get really close, right? Using the virtual scribe lines concept, right? And surely you can get a heck of a lot closer than you could with actual scribe lines, but we can do even better. So let's say that it is time to machine that line and produce whatever dimension that happens to represent. Well, what we can do is we can use radar mode. Okay, and I can go to radar, and I can say normal, and now I can say find the closest entity. So notice that that entity turned red. That means that it's on radar. So that means that this D equals 0.0542, that's how far I am from the line, right? Everywhere I move the tool, D updates itself. So that means that if I wanted to finish that line, all I got to do is drive D down to 0, right? And now I'm exactly mathematically, geometrically on that line. Whatever dimension that thing happens to represent, I am now producing it. Okay, so that's really the money shot of this system. The fact that you can position the tool exactly with respect to the geometry, and now I'm finishing that line without even knowing what dimension that is. And so that's radar mode. Okay, so let's just do a quick little example here without actually cutting any metal. So let's say we did indeed want to machine the perimeter of this part. First thing I'm going to do is I'm going to rotate the part to -90 degrees, and because I just happen to know that that's where I want to start. Now I got to get the tool down there. Okay, let's just imagine that the part's already been roughed. So I'm going to go right for, notice that this line is still on radar, so I'm going to go right for radar 0, right, D equals 0, and that's close enough. So now I can machine along that line, right, I'm finishing whatever dimension that happens to be, right. Now I'd probably get the tool up out of the part because I'm about to rotate it, so I hit next, because that's the next entity, and I'm going to say align with X, and notice that the table is taken off and the part is rotated to whatever angle that thing happens to be on, and I'm going to again go for D equals 0, radar 0. That's close enough. So now I'm going to machine along this line. Probably not that fast. And I'm going to stop right on the y-axis, right where X equals 0, because I happen to know that that circle is right on center of the physical center of rotation. So once I get to the y-axis, see, close enough. Now I'm going to rotate the table and cut around this arc. So I'm going to go to Menu, Rotate Part, 281.089 negative. You have to have these angles all worked out beforehand. I'll show another time how to do that. But I just have these numbers all written down. So 281.089, go, okay. Now the table's rotating, and I'd be cutting around that arc, and I'm going to end up here. It doesn't animate the rotation on the screen, although that would be kind of a nice feature to put in one of these days. All right, next, that was the next entity, that arc. Next is this line, and you see I'm already almost exactly in tolerance with it. I'm within 3/10. Right, so now I can cut along this line. Next is this line here. You can move the display around to your heart's content to get your best view. And I'm going to stop when my radar is 0. Close enough. Now I'm going to get the tool up out of there, and I'm going to go Menu, Align with X. Good. Now I can get the tool back down into the cut, and I'm going to go for radar 0. And first thing I'm going to do is I'm going to go backwards to this last entity and just get into that corner, right? So I'm going to go to radar 0 here with the previous entity. So now I know I'm exactly in that corner. And when you're going for these corners, I never go exactly to 0. I stay, once it falls below 1,000ths, I just walk away and get out, because you don't want it to undercut or anything like that. Okay, next. So now I can machine along this line. Next. Now I just go, notice that it's negative. It's because technically I'm violating that line. That line would be going up through the cutter. So I want to go till I'm 0 or positive. Then I know I'm on that side of the line, right? So there it is, 3/10 away from it. Close enough. Now we're machining this dimension. Okay? And voila, we've just machined around the entire periphery of the part, using radar to get the tool within you know, 0 or within a tenth or two of each entity. And so we've just produced all of these dimensions without even knowing what the dimensions are. Okay, we've covered a lot of ground and yet just scratched the surface. So to recap, the process starts with a CAD drawing. I'm sure that this isn't going to show up on my camera. So you start with a CAD drawing. Any CAD system will do, and as long as you can save your file as a DXF file. And then the model is transferred into the Cartesian display. So remember that this is not just a picture of the part, it is the CAD geometry. So the Cartesian display has in its memory the exact mathematical model of the part. It's the same as the CAD model. And then we showed how you can manipulate the tool around, you know, the motions of the machine, and the cutter moves in real time with response to your machine, your hand inputs. And you can move the tool with respect to that geometry, and you can zoom up on it, and you can get the tool as close as you want to those lines and actually machine a part with just going by the scribe lines alone. And I think you'd call it like virtual scribe line mode. Remember, that's like the nickname of the system. But we can actually do a lot better. By using radar mode, you can position the tool exactly with respect to a given entity. And remember down here we had D equals some distance, and that's telling you the distance that the tool is, the edge of the tool is from that surface. So when you put it at D equals 0, you are exactly mathematically on that line, whatever dimension that happens to represent. So now when you machine along that line, you're producing that dimension, without even knowing what the dimension is, of course. And then next we showed angled lines can be machined by simply putting that angled line on radar and telling the system to rotate to align that, that line with X or Y axis. So you can say align with X or align with Y, whichever one you want to move. So once it's parallel to the X or Y axis, you can machine along that line. Now you're cutting that angle and whatever other dimension it happens to represent. And without knowing the angle, by the way, because the angle is embodied inside the model of the part. And so when you tell it to align with X-axis, say that it computes what angle it needs to move to, and it communicates that to the rotary table controller. And the rotary table does the rest. And finally, this is actually kind of a special case, this part, because the fixture that holds it, this arc here, is on center with the physical center of rotation of the table and the origin, the geometric origin. So that means when I rotate the table, I could actually be cutting that arc perfectly. And also this little interior arc segment here. And you have to actually know the angle, the start and stop angle beforehand. And I'll show another time how to work that out. And I was keying in the angles, and you can actually get the display to remember the angles for you, but I kind of like keying them in and do it either way. So let's go ahead and cut a real part now. Okay, let's get it on. Okay, I'm going to start at -90 like I did before. Find. Okay, got radar, bring it down to about 10 thousandths. That's good. Tool up. Next, menu, align with X. stop right on the x-axis, on the y-axis rather. Close enough. 281.089 negative. Now we're in the perfect position to machine along this line. And notice when I put the radar focus on that line, it indeed still shows about 10 thousandths. 11. Close enough. And that's all because this circle is on the same center of rotation as the rotary table. So, like I said earlier, this is kind of a special case. But I like it because it shows almost everything that the system can do all in one little part. Next. Good. Tool up. Align with X. Okay, I just want to go 10 thousandths beyond this line. Good. Okay, done. So the periphery is roughed. Okay, now we're ready to finish the perimeter. Okay. Go for radar 0. Close enough. Now I'm finishing that dimension. Okay, tool up. Next, line with X. Alright, good. Minus 3/10, that's pretty close. It's fine. Stopping right on the y-axis again. Okay, close enough. Okay, now this time the angle is 461.089 negative. And once again, we're in the perfect position to just take off along this line. Tool up. Line with X. This time I'm going to come at it from the outside here. So I'm going to conventional in and then climb back. Okay. Now climb back out. Next. Go back to D equals 0. Okay, good enough. Okay. Alright, now we've roughed and finished the outer perimeter. Now we're ready to do the inside. Find $10,000 is good enough. Now I'm going to ramp down into my depth of cut. Okay, I'm in. Just going to go by eye on the roughing pass here, up into this corner. Close enough. Okay, tool up. Line with X. I'm going to zoom in here now. I'm just going to kind of etch-a-sketch my way around this arc here to rough it out. That looks pretty good. Next, get the tool up out of there. Align with X. Okay. Back down to depth. Now this time we're going to align this line with Y. Align with Y. Okay, now we're going for radar 0. Get down into the depth of cut. Put the coolant. Okay. I'm just going to do this by eye again. It's close enough. It'll look good. Close enough. Tool up. Align with X. Tool down. Backing into the corner, using the previous entity to know where to stop. Good enough. Next, okay. Good. Okay, now this time the angle is rotate part 486.6 negative. Okay, tool up. Next, align with X. Tool down. Previous, so I can back into that corner a little bit. Close enough. Next. put that entity on radar so I know where to stop. Tool up, cool it off, and we're done. We've roughed and finished the interior perimeter. Okay. All right, that wasn't so hard. It looks good. Okay. Beautiful. We're done. And look at all those chips, by the way. That is money right there. When's the last time you saw a Bridgeport make these kind of chips? It's amazing. Okay, so let's take a look at some results here. I got this part all cleaned up and deburred. I'm just going to take a couple of dimensions here. Some of the more obvious dimensions, like this one, 2.21. Looks like 2.21 on the nose. Let's try 0.750. And that is 750 on the nose. 0.3. Looks like 0.301. 301 and a couple tenths. 301 on the nose. How about the other side? 301 about. 0.301. And finally, this diameter here is 1 inch. And it looks like it's about 0.999. So all these dimensions are, I'd say, plus or minus 1, which is really remarkable. I mean, those are kind of tolerances you'd get, you know, if this thing had been done on a CNC machine. And without even trying, and with, again, no in-process measurements or adjustments of the machine. And so I'm calling that a success. Well, I hope you've enjoyed this little demo on the efficacy of the Tactical Cartesian Display System, especially when interfaced with a computerized rotary table like this one. So what is this system good for, really? I think it's good for doing things like prototypes, one-offs, short production runs, cases where you don't want to take your CNC machine offline to do one or just a few parts. And let's face it, a part like this, you're not doing a part like this on a Bridgeport. What are you going to do? You know, put a piece of stock in a vise and use scribe lines to machine it? It just isn't going to happen. Let alone part after part after part like I've shown, and holding tolerances that are basically unheard of, you know, in manual machining. And also believe that it elevates the usefulness and the productivity of the humble knee mill to a level that, frankly, historically, I doubt it's ever enjoyed. And it doesn't start, you know, with parts like this. I mean, you know, here's a case of a part. This actually is part of this little motor adapter here. And it's indistinguishable for something that has come off of a CNC machine. Look at these blends of these radii and these angles and stuff like that. And like here's the whole motor adapter. Nobody's machining something like this by hand. It's unheard of. And so I think that this system, for me personally, also brings a level of excitement back into the craft of manual machining, and that it could really use. And I've enjoyed using it, and I hope it catches on. So thanks for watching. Hope you enjoyed it.